that mean when you get down to it? Does it mean that if I've just flipped a heads, the next one will flip as a tails? Well, no, because these probabilities are independent of each other. One coin flip doesn't affect the other. So what does that 50-50 number really mean? Well, one way you could look at it is if you were to flip thousands upon thousands of coins, the more coins you flipped, the closer the number of heads to the number of tails would trend to being the same. So if you were to flip 10 coins, you might get 7, 3, 8, 2, even 9, 1 perhaps. But if you were to flip 1,000,000 coins, it would be as close to 50-50 as makes no odds. The bigger the number of iterations, the closer you're going to get to that figure. So that's really what probability is telling you. If we do this again and again and again, what are the percentages that we can expect? We can consider this with unstable nuclei. Each nucleus might decay at any moment, and they vary. Some, on average, will last a really long time, some a really short time. But that's just an average. You might have a nucleus of something very, very unstable that normally goes in a second, lasting for years, because it just happens to be the nuclei that's really, really strange, and just keeps trucking along and not decaying. On the flip side, you might have something like a uranium nuclei, which on average sticks around for hundreds of thousands of years, that might just decay. You never know exactly what's going to happen to one nucleus, but you can make predictions about massive numbers of them. Exactly the same way, you can't predict what will happen when you flip one coin, but you can make predictions what will happen if you flip 1,000,000 coins. So that's what's going on. Each individual nucleus, independent of the other nuclei, might decay at any moment, and that's a random thing, but we can make predictions about big numbers of nuclei. So, different unstable nuclei have a different value of lambda, which we call the decay constant. And that is the probability in a unit time, which will be a second, because we're using SI units, the probability in 1 second that a particle will decay. So let's imagine that we've got a lambda of 0.5. That means you've got a particle every second, there's a 50% chance it will decay. So what does that mean? If we've got a kilogram of the stuff, well, a second later, on average, half of them will have decayed, and you'll have 500 grams. A second later, you'll have 250 grams, and 125, and so on and so forth, because each individual nucleus, well, it's got a 50-50 shot in a second, and there's millions upon millions of them, so it's going to trend that way. This decay constant can be very, very high, very, very low. Example of something with a very, very high decay constant, it's almost certain to decay in a second. Well, there's lots of weird, strange subatomic particles that tend to stay around for nanoseconds or microseconds. So they're going to have a really, really high lambda. It's very, very likely they'll decay within a second. Then you have other particles, such as uranium nuclei, which this will be 0.00001, because they tend to stay around for hundreds of thousands of years. So lambda is going to be very, very low, very, very unlikely. We can imagine the change in the number of particles with respect to time is going to be equal to minus the decay constant times the number of particles. Why minus? Because the number of particles are getting lower and lower. We're not gaining particles, we're losing them as they decay. So again, if this was 0.5, the change in the number of particles divided by the change in time, well, half of them are going to go every second. So the equation works easy peasy. So by looking at lambda, we can work out how many particles there are going to be after a certain amount of time. We can also calculate how many decays we're going to get in a certain number of time. We call the number of decays per second the activity. So the activity is number of decays per second. It's given the symbol A, and that's easy. It's just going to be equal to lambda n. N number of particles, lambda the odds of one decaying in a second, therefore the activity, very simply, is just going to be those two numbers multiplied together. if I've got 1,000 particles, and there's a 50% chance one will decay in a second, well, my activity is clearly going to be 500 decays per second. Simple as that. Activity is a measure of really how radioactive something is. It's obviously going to be a combination of these two things. It's very, very safe to be near uranium because the lambda is incredibly low. However, if you built your whole house out of uranium and there were kilograms upon kilograms of it around, well, you might start to get a bit irradiated just because the N's so big. On the flip side, you get something really nasty, like one of those fluorine isotopes where the lambda's through the roof. You're not going to need very much of it to get a big radiation dose. So it's clearly a combination of these two things that tell us how radioactive something is. There's one last thing that you need to know. And that is, what affects lambda? And the answer is, this is nuclear physics. It's purely how they click together inside that nucleus. So make sure that you don't think it's got anything to do with chemical bonds between electrons. If I take a uranium atom and I put something very reactive next to it and I form some chemical bond, I don't know what its chemistry, but I presume you can make uranium something. It's not going to affect this decay constant at all. The nucleus doesn't know what the electrons are doing. From its point of view, they're infinitely far away. You know, this is femtometers, this is micrometers. So, you know, orders of magnitude difference. So that's the first thing. Also, temperature isn't going to affect it because that's a measurement of how much particles moving around, but that's not going to affect the ratio of strong nuclear force to charge, which is, of course, what makes things decay or not. Finally, you need to know something called half-life. Now, you may have heard of half-life before, probably played the computer game. Half-life is defined as the amount of time, on average, it takes for half the stuff to disappear. So it's easy with lambda of 0.5, but if it's a different lambda, you're going to have to work that out. And it's extremely simple. It's just the natural log of 2 over lambda. So if you work this out, you can calculate, on average, how long it will take for the mass to halve. Where this comes from, well, that's clearly an exponential curve.